Swayam Prabha. Digital India. Educated India.
Hello, welcome to the class of high performance computing for scientists and engineers. We are continuing in our first module, which is fundamentals of parallel computing, and this discussion will be on shared memory and distributed memory for parallel computing. In last few sessions we have discussed about computer architecture, parallel computer architecture LC, and during that discussion the concepts of all the computers sharing a same address space, which is called a shared memory, and each CPU is connected with a different memory unit, and they do not share the same address space. Each memory unit is independent of others, which is called a distributed memory. These ideas came up, and we will see some of the details on that. And we have also seen what are the communication costs overhead in different type of memory architecture, but we will have some more detailed discussion on it today, and we will then see what are the applications of this application. So, we finished about Flint's taxonomy. So, in last class, so what we will do today, we will see that shared memory and distributed memory computers, how do they lie as per Flint's taxonomy. We will look into shared memory machines and one of the important issue called cache coherence, which you can remember that in the second and third lecture we discussed about cache coherency and what are the what is the issue exactly and how this can be handled, and some the pros and cons of shared memory. We will see what is the main issue in distributed memory, that is message passing in between computers, and again look into the pros and cons. And this is important because as an application engineer of high performance computing, you need to decide that how do you want to put higher performance in your program. How you have a sequential program, you have a program which runs in single computer, and how do you want to make it parallel, which type of architecture you will use and which type of memory you will use. You have to make a decision on that, and that is why it is important to see that both shared memory and distributed memory platforms are available to you. We assume the fact, and then how which one you will choose based on your application. So, the pros and cons are important to know, and then we will see a matrix computing, some of the matrix computing algorithms, some very basic matrix computing operations like vector dot product, matrix vector product, etc. And both in shared memory and distributed memory, how to do the memory management if we think of parallel implementations. Well, so as per Flint's taxonomy, we have seen processor architecture can be classified in 4 classes: single instruction, single data stream, SISD, which is a sequential computer. We will not discuss it much further because we are trying to get higher performance, which we will of course not get in single instruction, single data stream computer. Single instruction multiple data stream or SIMD, multiple instruction single data stream or MISD, and multiple instruction multiple data stream, sorry, this will be MIMD. Sorry, there should be some changes here. This will be MIMD, wrongly written as SISD. This should be MIMD. Well, the first one is uniprocessor, and again we are not, is a single processor connected with the single memory unit. It cannot do anything in parallel. We are not discussing about it any further. These two, single instruction multiple data stream and the single instruction multiple data stream and multiple instruction multiple data stream, they are used in HPC enabled scientific computing. So, we will discuss about these two schemes, that single instruction multiple data stream and multiple instruction multiple data stream in detail. Well, so single instruction single data stream has basically two types of computer hardware are used in this to follow this architecture. One is vector processor, that all the computers are working on different elements of a vector. So, a vector processor given a like a sequential computer writes a plus b is equal to c, a and b are scalars and c is a single valued scalar. A sequence vector processor will write ai plus bi is equal to ci, and these are for i's which are of all the elements of that particular vector. And an array processor, that means multiple processors are connected via bus to the same memory unit. The array processor, we have seen it in few of the first lectures, that there is a particular CPU which connects to many processors. Each processors have their again connected to an interconnect network switch, have their separate own memory unit. However, all these memories map to a same memory space and a physically same memory. So, they can operate on different data, but they will operate it on the single memory unit on the same shared memory location. Then comes multiple instruction multiple data MIMD. There can be two different variants of MIMD. One is MIMD using shared memory. They are using same address space, however, the memory units are they are using same address space which can be, however, they can do multiple operation on different data. They can do different type of operations on different data. One is a symmetric multiprocessor, where many processors are connected via a bus to a same memory unit, and each processor can take different locations of the memory unit. It is the same memory, but there will be different locations of the address space and do different operations there, and it is called an uniform memory access or UMA, because it is a uniform memory which all the processors are accessing. Then can be distributed multiprocessor or non-uniform memory access, that there are different processors which have their own cache and own memory, and these processors are connected through an interconnect switch, and all these memory units, though they are physically different memory units, but all these memory units are some way mapped into a common shared address space. All these memory units are mapped into a shared address space. So, even if we see a variable a here, there are vector a here, there are few elements of the vector a, the next elements of the vector a lies in the other memory units, that each of the processor through that interconnect switch can communicate among them and see the parts of the other memory units also, of the same parts of the memory which is lying with the other physical RAMs. Well, and the third one is a cluster, which is a distributed memory system, that you have a Ethernet by which you can connect many computers, and all these computers are also connected through a high speed switch, and each computer is as a physical computer. It has its own memory, own processor, own CPU and own memory, own cache, etc. They are pointing to different memory units, but these memories are not sharing any common address space. They are pointing to different disjoint address spaces. So, if it has a variable a, if the first processor has a variable a, the next processor also can have a variable a, and these two variables can be completely different from each other. So, this is a distributed memory, distributed MIMD system which has decoupled address space. For the shared memory, it is the same address space. For the distributed memory, is a decoupled address space. However, we can have MIMD using both of these, and we can have SIMD using array processor or vector processors. So, it is different architecture, both in terms of hardware as well as in terms of program which can be implemented to follow Flint's taxonomy. So, we come to shared memory machines. The features of shared memory computers are: the general feature of a shared memory parallel system is that all the processors point to a common global address space. They may be connected to a same memory unit, they may have different separate memory unit attached with different processor. However, the address space is same for the processors. Even if some of the memory is physically located at some of the disjoint memory units, they are treated as a same common memory space. Like if you go to your computer and say you have a 16 gig RAM, where you see that 4 RAM cards are there, that 4 GB RAMs are connected, and 4 into 4 you are getting a 16 GB RAM. If you have a variable which can span up to this, any variable can span up to this 16 GB space, it will be, though they are separate units, it can be considered as virtually as a same contiguous piece of memory. Similarly, even if these shared memory systems, they are NUMA multiprocessors, they have different memory units for different processors, they are pointing to the same address space. And for uniform memory access, it is the same piece of memory which is connected to which all the processors are connected. So, both physically as well as from the memory management perspective, they are pointing to the same address space. So, shared memory means it is the same address space which is shared between different processors. Therefore, any change in memory by one processor is reflected in all other processors. If A is a variable array and some of the element, a third element of A is changed by some processor, processor A, 18th processor changes the third element of A. All other processor sees that this value has been changed. So, any change, it's the same memory which all the computers are connected with, all the processors are connected with. So, all processor is seeing any change made by one processor must be visible to all other processors. If they are connected to same physical chunk of memory, they are called uniform memory access or UMA system. If the computer has different memory pointing to same global address, it is called non-uniform memory access or NUMA. Shared memory MIMD uses both private and shared data for each processor. So, some data can be private to the processor, that means it is not a shared memory, not in the shared memory space, not in the common memory space. It is some data which is only known by the processor, and other processor can have similar data like this. However, this is a small amount of data which is usually used for writing the loops, setting the parameters, etc. If shared data is cached, and we need to use cached systems for better performance. Again, if it is cached, then the memory bandwidth requirement is reduced. So, it is important, it is good to have cache in shared memory MIMD systems too. But in case you have cache, there is an important issue called cache coherency, which is very important in terms of the overheads and operation of a shared memory cached system. We will see what is a cache coherent system. Say there are two processors, processor 1 and processor 2. They have their own caches and they are connected to, after the caches they are connected to a large memory system M. Now, there is some variable x in the memory system, and this processor, both the processors will operate using that variable x. So, the first operation while doing, say we have both the processors are asked to do x is equal to writes x plus y, read the value of x from the memory, add it with some y and return the answer. So, both will be, they are working in parallel connected to the same memory unit. So, both will be asked to read x. So, they will go to cache and ask cache what is x. Cache will prefetch some of the data, say x is equal to 5. So, this x is equal to 5 is prefetched and already lying in the cache. They will read what is x, they will read x is equal to 5. Both the processors register will now know that x is equal to 5. And then the processor 1, and we talk about a multiple instruction system. Processor 1 is asked to do x is equal to x plus 3. Processor 2 is asked to do x is equal to x plus 5. So, processor 1, as it does x is equal to x plus 2, its cache will do it x is equal to 8, this x, and second processor will do x is equal to x plus 5, its cache will write x is equal to 10, and any data in cache will be reflected. So, x is equal to 8, sorry, x is equal to 8 goes to cache, x is equal to 5, x is equal to 8 goes to cache, sorry, and x is equal to 10, the same variable x which is being changed by processor 1 as x is equal to 8. Now, it is x is equal to 10 is lying in the cache, but it cannot go to the memory because the memory has been written by x is equal to 8, and that's therefore, we can see that there is a conflict because the same variable x, but their caches have different values. So, either it will overwrite it, that means this operation will go in junk, or it has to do something to establish coherence. So, we need cache coherency. So, when one variable is updated, it is updated uniformly in all the caches. So, what can be a cache coherent way? That it reads x, x is equal to 5 is there. The first processor writes x, operates x is equal to 8, which when one cache is modified, the other cache has to wait till it goes to memory and comes back here. It has to wait to the cache update by first processor to the memory, and again cache being updated by from memory to the second processor. Processor will wait till the cache update is finished. So, though it is a parallel program, processor 2 cannot move in order to have coherence in cache. So, x is equal to 8 is in processor 1's cache, it will go to the memory, it will come back to processor 2's cache, and processor 2 will now operate x is equal to x plus 5, it will be x is equal to 13, x plus 5, x is equal to 13. This will go to the main memory, this will again get back to the first processor's cache. Now, there is coherence everywhere. So, what happened? The second processor goes through an idle loop, otherwise there was a stalemate. First processor has changed the variable, second processor has changed the variable differently, same variable has different values in different cache, it cannot go any further. I mean, there is a problem, it is a conflict, you cannot do anything, but here things can be updated, right? X is modified by both the processors. So, what was the initial x to which both the processors additions are done, but the first processor, well, the first processor has operated, second processor has to wait for a while. Once this cache update is done, then only it can work. So, there is a wait time by the second processor which is introduced, and there is some sequentiality. The processors now actually cannot work in parallel. What they have done in parallelly their caches have read the same variable, but they, well, some of the efforts are saved. Otherwise, if the single processor is doing it every time, going it back and changing the cache, adding it, it probably would have taken more time, and not every time they are operating on the same variable. So, some point of time they are operating on the same variable when one processor has to wait, but you cannot avoid it to establish cache coherency. So, processors operate sequentially to ensure cache coherency, and there are some protocols to establish cache coherency. These are called Snoopy cache or directory based updates. One protocol is Snoopy cache, that means if there is any change in the cache by any of the processors, that particular memory sectors will be identified, and the system will try to see where does this particular memory unit lie, in which computers have the same pointers, same memory pointers are in their cache, and that part of the cache will be updated in all the computers. Or the directory based protocol is that again, if some of the variables are in different computers cache, it will be identified first, and this will be handled separately. So, using these protocols, cache coherency is established, so that what I saw as sequentiality in between the processors, they can be avoided in certain cases. If there is no cache conflict in between the processor's operation at one particular go, then they can run very much in parallel. So, this also has to be ensured via these protocols. There can be another aspects, we'll probably discuss it some point of time later, that consider a case that cache is not a single variable. Cache contains prefetches data in an anticipation that these are the next data which will be used. So, it fetches a line or a set of variables, a line of array. So, x has, instead of x, let us operate on array A, an array A. So, A has say 30 elements, and first 5 is being operated by processor 1, the next 5 is being operated by processor 2. Processor 1 changes something in the fourth variable of A. However, fourth variable, when it is operating on fourth variable, the cache has taken probably few more variables also of A also. So, it has taken a line of A, some of which, though actually the variable on which processor 1 is working, that is not shared with processor 2, but cache has taken a line, some of the elements of the lines are also in the cache of processor 2. So, they have to follow some Snoopy cache or some of the protocols, some sequentiality, because they are sharing the same cache line. One modifies something on the cache line, the others have to wait till that operation is finished and reflected. It is called a false sharing, though the processors are not sharing actually any value, but they are sharing a cache line, and one is modifying the cache line, other has to wait for cache coherency. It also adds to overhead. Overhead means the parallel cost of computation, cost of communication increases, and as a whole the cost of computation increases, the parallel efficiency reduces. We need to discuss about parallel efficiency later, keeping this in mind. So, in multiprocessors, so for processor array or for uniform memory access system, symmetric multiprocessors, SMPs, it is it can be found out that it is the same piece of memory, therefore, cache update is coming from the same piece of memory, which is fine. But for non-uniform memory access multiprocessors, caches at individual nodes are updated, and this update requires that there is some change in the memory unit associated to some other processor, but this processor's memory has to also be changed to ensure cache coherence, which is done through migration, that each reference data, when some data is changed by one processor, it will migrate to the cache at a node. From each of the reference data from one processor, the data will go to the cache also. And if data is being simultaneously read by two processors, then a copies will be made at each node, which is called replication. These are used for ensuring proper cache access in distributed multiprocessors on NUMA. And cache coherent protocols are again required to ensure that the updates are valid. So, nobody is overwriting something which should not be overwritten by one, because it is changed by other processor and resides, none of the variables should reside differently in different caches. Write, and the protocol is cache coherent protocol is that one write is not complete unless all the processors have seen the effects of write. So, if one processor is asked to do x is equal to x plus 5, the new x should go to the shared memory space and should be communicated to the cache of all the other processors which are using same cache line. Before that, we will not say that x is equal to x plus 5 is complete, that we will say that this is complete and the processor can now go for the next steps. Processors does not change the order of any write or with any other memory access. So, if there is some order of writing some of the variables is given, first it will be done, then the other memory access reading etc. can take place, and this also ensures cache coherency. So, this is that it is actually adding overheads. Instead of the processor being free to do its own work in its own way, it has to wait till the variable is migrated and the changes are reflected in the cache of the neighboring nodes. It adds to the overall computing time or communication time also. So, we will see these are very important aspects of shared memory. Now, we will see what advantage and disadvantage of the shared memory system. The advantage is that they are sharing a common global address space. So, if you write a variable a, it is known to all the processors. You really do not need to think that same variable can have different meaning at different processors, except for some of the private data, for the main part of the data. So, it is a more programmer friendly platform. A programmer knows that if I have discussed a variable, it is everywhere. It is known by, if I have declared a variable, it is known by all the processors. Proximity of the memory to the CPU is much closer to the memory of CPU is much closer to the RAM, and this makes data sharing both fast and uniform. So, there can be cases that CPU, the memory is connected via bus for uniform and symmetric centralized multiprocessors (SMPs), and they can be connected by interconnectors also through different units. However, the memory units are very close to each other. These are very closely packed system, and especially for uniform memory access, when they are reading from the same memory unit, the reading is very fast and it is uniform also. The disadvantage is that, so one of the important is that programming wise it is easier to handle shared memory, and also the communication overheads are less because the data sharing between the processors are fast and uniform. Disadvantage is lack of scalability. If we keep on adding more CPUs in the system, it is the same memory which all the computers are accessing. Therefore, the traffic on reading the memory or writing the memory increases, because it is the same piece of memory, it is almost contiguous locations which different processors are trying to access, and there can be a lack of bandwidth. For cache coherent systems, adding more CPUs adds to more overhead, because this cache memory management has to be established by different CPUs. It adds to further adds to the overhead. Programmer has to put special effort for synchronization to ensure correct statements, because again caches may ensure that some of the statements may not be correct. So, programmer has to put special effort for synchronization, so that the cache update, cache coherence is established, while not executing any incorrect or invalid statement in the program. Well, so we have discussed about shared memory and cache coherency and the pros and cons of shared memory. In the subsequent class, we will discuss about the distributed memory systems. Thank you.